Hi, my name is Aran Brady and my project is entitled to achieve at least a CCA S1D1A1 classification on FP200 gold when tested to BS EN 50399 by means of compound development. EN 50399 was a test brought in by the EU in 2016 under Construction Products Regulation. The test consists of applying a flame to several vertically mounted cables on a ladder, then analysing the flame spread, heat release, as well as acidity, smoke production and occurrence of flaming droplets, as shown on the project poster. A classification from F to A is then given, depending on the final test result, with each class having stricter parameters which must be met. Prysmian flagship product FP200 Gold, when tested, results in a D classification. The problem with this is that Prysmian's commercial team believe that this will result in loss of sales and therefore market share. Therefore, we need to achieve at least a C. The solution was to develop the existing compound to improve its flame propagation properties to achieve at least a CCA classification in the EN 50399 test. To find the solution, two phases of research and development were conducted. The first phase was a small-scale thermal analysis of each of the three fire-inhibiting ingredients within the existing compound. The aim to see what combination of these ingredients resulted in the best thermically stable compound. From here, 16 30-gram samples were made and the following observations were made as shown on the project poster. Firstly, magnesium trihydroxide appears to be a better all-round performance as a mineral filler than aluminium trihydroxide, and as expected, the higher amount, the harder the ash at the final result. Nanoclay appears to be a better trial promoter than carbon nanotubes, and it works better between 17 and 25 parts per 100 resin, but it's more cost effective at 17. And hologlass micropheres are also a better glow suppressor than zinc borate, and again these are better used at 10 parts per 100 resin instead of 5. Phase 2 developed on the findings of the first phase and incorporates all the other ingredients to manufacture 5 recipes that could be used for full-scale production. These samples were again analysed using several techniques, one of which was oxygen index, whereby a moulded sample is placed into an oxygen chamber, a flame is applied, and this flame must go out within 3 minutes to pass to that oxygen percentage. The higher the oxygen percentage, the better the flame propagation properties of the compound. As shown on the poster, recipe 18 was chosen as this has the highest OI, but did have the lower mechanicals and lower melt index than the standard compound. For phase 3, a 750 kilo batch of the recipe was compounded and then extruded to manufacture cables. 2 different size cables were manufactured, and during these stages observations were made of how the development compound differed to the standard. As shown on the project poster, the development compound has slightly higher screw RPMs during compounding, as well as slightly higher screw RPM and amps during extrusion. However, the development compound was able to meet the maximum line speed on both occasions. Finally, phase 4, both fire testing and mechanical tests were conducted on both the samples, both of which passed the standard required for the cable, BS7629, and they also met the scope of the project to achieve at least a CCA S1D1A1 classification, again as shown on the project poster. During the project, I found the most interesting part the first phase, as I've not used these techniques before, and I found it really interesting and I've used them since, so I found that really beneficial. The most difficult part was having the time to do the first 2 stages, where I had a lot of other work on at Prysmian at the time, which meant it was brought back by 3 or 4 weeks. Thank you for listening.